On a clear morning in 1962, a Soviet test pilot strapped himself into the cockpit of a Su-9 Interceptor, performed standard pre-flight checks, and initiated what should have been a routine high-altitude intercept mission. The aircraft's turbojet engine spooled to operational parameters. Hydraulic systems pressurized normally. Flight control surfaces responded to input commands. All instruments indicated nominal performance across primary systems. The pilot followed established procedures, maintained prescribed airspeeds, and executed maneuvers within documented flight envelope limits. Within 30 minutes, that pilot would be dead. This was not an anomaly. Across multiple test facilities and operational squadrons, Su-9 pilots reported consistent patterns of system behavior that defied conventional aviation safety margins. Aircraft that passed ground inspections suffered catastrophic failures during routine operations. Ejection systems that functioned perfectly in static tests failed when pilots needed them most. Flight control responses that appeared stable in simulation became unpredictable at operational altitudes and speeds. The Su-9's reputation emerged from a fundamental contradiction embedded within its design architecture. Engineers had created an interceptor that could achieve its mission parameters while simultaneously creating conditions that made pilot survival probabilistic rather than assured. Training protocols taught pilots to operate within system limits that existed theoretically but proved unreliable in practice. The aircraft functioned according to specification, yet those specifications contained assumptions about pilot capability, system redundancy, and failure recovery that reality consistently violated. How can an aircraft perform exactly as designed while making pilot death a predictable outcome? The answer lies not in mechanical failure or pilot error, but in the collision between design philosophy and physical reality. The Su-9 represented the apex of Soviet interceptor doctrine, an aircraft optimized for a single mission parameter, the destruction of high-altitude strategic bombers, without regard for the operational constraints that reality imposed on both machine and pilot. Every design decision, from engine selection to control system authority, reflected assumptions about acceptable risk that proved systematically invalid when subjected to the physics of high-speed, high-altitude flight. The aircraft's primary power plant, the Tumansky R-13 turbojet, embodied this fundamental contradiction. Soviet designers prioritized raw thrust output over operational controllability, creating an engine that delivered exceptional performance at the cost of predictable power delivery. The R-13 produced thrust-to-weight ratios that exceeded the control authority available through conventional aerodynamic surfaces. At operational altitudes above 15,000 meters where the Su-9 was designed to intercept incoming bombers, the engine's power output could overwhelm the aircraft's ability to maintain controlled flight. This was not a design flaw in the conventional sense. The engine performed exactly as specified, delivering the thrust necessary to achieve intercept velocities exceeding Mach 2. The problem lay in the assumption that pilots could manage the transition between engine power settings while maintaining aircraft control. The R-13's throttle response characteristics created power delivery curves that changed dramatically with altitude and airspeed. At low altitudes, throttle inputs produced predictable thrust changes. At operational altitudes, the same inputs could generate thrust variations that exceeded the pilot's ability to compensate through control surface deflection. Soviet aerodynamicists understood this relationship in theory. Wind tunnel testing had demonstrated the control authority limitations inherent in the Su-9's design. However, these limitations were considered acceptable given the aircraft's mission requirements. The interceptor was designed to engage targets in straight-line intercepts, not to dogfight or perform sustained maneuvering combat. The assumption was that pilots would fly predetermined intercept profiles, fire missiles at maximum range, and return to base using carefully planned flight paths. This assumption ignored the realities of operational flying. Test flights, training missions, and even routine intercept sorties required pilots to deviate from predetermined profiles. Weather conditions, equipment malfunctions, and tactical considerations regularly forced pilots to operate outside the narrow envelope where the Su-9's design remained controllable. The aircraft's flight control system provided no graduated warning when approaching these limits. Pilots received no indication that they were transitioning from controllable to uncontrollable flight regimes until control authority was already lost. The Su-9's flight control system represented another critical assumption that proved systematically invalid. Soviet designers implemented a purely manual control system, assuming that pilot skill and training could compensate for the aircraft's inherent instability at high speeds. The control system provided mechanical linkages between pilot inputs and control surface deflections, with no artificial stability augmentation or electronic intervention. This design philosophy reflected the Soviet belief that pilot skill represented the primary safety system. The mathematical reality contradicted this assumption. At Mach 2 flight speeds, aerodynamic forces on control surfaces exceeded the physical capability of pilots to generate sufficient control inputs. The Su-9 stick forces increased exponentially with airspeed, creating conditions where pilots could not generate enough force to move controls effectively. Simultaneously, the aircraft's center of pressure shifted aft at high speeds, creating natural instability that required constant corrective inputs to maintain controlled flight. These characteristics were documented in test reports but were considered manageable through pilot training and operational procedures. Flight manuals specified maximum control deflection rates and provided guidelines for maintaining stability during high-speed flight. However, these procedures assumed that pilots would always have sufficient time and situational awareness to implement corrective actions. The procedures did not account for the physiological limitations of pilots operating under high G loads or the cognitive demands of managing multiple system emergencies simultaneously. The aircraft's structural design reflected similar assumptions about acceptable stress margins. Soviet engineers calculated structural load factors based on normal operational maneuvers, adding safety margins that were considered adequate for military operations. However, these calculations assumed that pilots would not exceed documented maneuvering limits, and that emergency situations would not require maneuvers beyond normal operational parameters. The Su-9's airframe could withstand G-forces up to 8.5 positive and 3.5 negative under normal conditions. These limits provided adequate margins for planned intercept maneuvers. However, pilots facing control system emergencies or engine malfunctions often needed to execute recovery maneuvers that exceeded these limits. The aircraft's structure would fail before pilots could regain control, creating situations where successful emergency procedures became physically impossible. Perhaps most critically, the Su-9's design reflected assumptions about failure mode predictability that proved systematically invalid. Soviet engineers designed redundancy into critical systems, but assumed that failures would occur in isolation and would be immediately apparent to pilots. The aircraft's hydraulic systems included backup pumps and alternate control pathways. The electrical system provided redundant power sources for critical instruments. Emergency procedures existed for every documented system failure mode. The flaw in this approach lay not in the redundancy itself, but in the assumption that pilots could accurately diagnose system states during high-speed flight. The Su-9's instrument panel provided indications for system pressures, temperatures, and flow rates, but these instruments reflected system inputs rather than actual control surface authority. A pilot could observe normal hydraulic pressure, while the system had lost the ability to move control surfaces effectively. Engine instruments could indicate normal operation while thrust delivery became unpredictable due to fuel system anomalies that were not directly monitored. This information gap created a systematic bias toward continued operation when immediate emergency action was required. Pilots trained to trust their instruments would continue flying aircraft that had already lost critical capabilities. The training assumption that instruments provided accurate state information led pilots to delay emergency procedures until recovery was no longer possible. The ejection seat system represented the ultimate manifestation of these false assumptions. The K-36 ejection seat installed in the Su-9 was designed to provide pilot escape capability across the aircraft's operational envelope. Soviet engineers tested the system extensively, documenting minimum altitude and airspeed requirements for successful ejection. The system functioned reliably within these parameters, providing pilots with a theoretical escape option when aircraft became uncontrollable. However, the ejection system's operational envelope did not align with the flight conditions where the Su-9 most commonly became uncontrollable. The aircraft's design flaws manifested most severely at high altitudes and high speeds, precisely the conditions where the ejection seat's reliability decreased dramatically. At altitudes above 12,000 meters, the seat's rocket motor provided insufficient acceleration to clear the aircraft's slipstream. At speeds exceeding Mach 1.8, aerodynamic forces could prevent successful seat separation from the cockpit. These limitations were documented in technical manuals, but pilots were not trained to recognize the transition points where ejection became non-viable. The seat was equipped with warning systems that indicated minimum safe ejection parameters, but these systems provided warnings based on instrument readings that might not reflect actual flight conditions. A pilot flying an aircraft with compromised control authority might receive normal ejection system indications while already operating outside the envelope where ejection could save their life. The training protocols developed for the Su-9 reflected and reinforced these design assumptions. Soviet flight training emphasized aircraft performance capabilities and mission accomplishment over emergency recognition and recovery. Pilots learned to extract maximum performance from the aircraft, pushing operational envelopes to achieve mission objectives. This training philosophy aligned with the Interceptor's mission requirements, but systematically underemphasized the warning signs that preceded loss of control. Simulator training focused on successful intercept profiles and normal operational procedures. Emergency scenarios were practiced, but emergency training emphasized procedural execution rather than rapid recognition of approaching system limits. Pilots learned to follow checklists methodically, assuming that sufficient time would be available for proper emergency procedure implementation. This assumption proved fatal when emergencies developed faster than procedural responses could be executed. The organizational culture surrounding the Su-9 program reinforced these training biases. Test pilots and operational squadrons were evaluated based on mission completion rates and performance achievements. Safety metrics focused on procedural compliance rather than recognition of systemic design limitations. Pilots who raised concerns about aircraft controllability or safety margins were often viewed as insufficiently aggressive or inadequately trained. This cultural bias created systematic underreporting of near-miss incidents and control system anomalies. Pilots who experienced control difficulties during flights would often attribute these incidents to pilot error rather than design limitations. Post-flight debriefings emphasized successful mission completion rather than detailed analysis of system behavior during anomalous conditions. Critical safety information was lost because the reporting system was not designed to capture systemic design flaws. The maintenance protocols developed for the Su-9 reflected similar assumptions about failure predictability and system reliability. Maintenance schedules were based on component life calculations that assumed normal operational stresses and predictable failure modes. Inspection procedures focused on documented wear patterns and known failure mechanisms. Maintenance personnel were trained to restore systems to specification rather than to identify marginal performance that might indicate approaching system limits. This approach proved inadequate for an aircraft that operated at the margins of controllable flight. Components that passed inspection criteria might still exhibit performance degradation sufficient to compromise pilot control authority during high-stress maneuvers. Hydraulic systems that met pressure and flow specifications might respond sluggishly during rapid control inputs. Engine components that passed thermal inspections might exhibit thrust variations during altitude transitions. The regulatory environment governing the Su-9's development and operation reflected the systematic nature of these false assumptions. Soviet aviation authorities established certification criteria based on the assumption that properly trained pilots operating properly maintained aircraft within documented limitations would encounter acceptable risk levels. Certification testing focused on demonstration of compliance with specified performance parameters rather than comprehensive analysis of failure mode interactions. This regulatory approach failed to account for the reality that military aircraft must operate in conditions that exceed normal specifications. Combat requirements, weather conditions, and equipment failures routinely forced pilots to operate outside certified envelopes. The certification process did not adequately evaluate aircraft behavior during these off-nominal conditions, nor did it establish criteria for pilot survivability when normal operational assumptions proved invalid. The fundamental error embedded within the Su-9's design philosophy was the assumption that complex system interactions could be managed through procedural compliance and pilot skill. Soviet engineers created an aircraft that required perfect execution under perfect conditions to remain safe. The aircraft provided no margins for human error, equipment degradation, or operational contingencies. Every assumption underlying the design, from pilot reaction times to equipment reliability to mission profile predictability, had to prove correct simultaneously for safe operation. The physics of high-performance flight made this assumption systematically invalid. At the Su-9's operational envelope, small variations in flight conditions produced large changes in aircraft behavior. Pilot workload increased exponentially as airspeed and altitude increased, precisely when aircraft controllability decreased. System failures that were manageable at low speeds became catastrophic at high speeds. The aircraft's design created a convergence of failure modes that could not be managed through training or procedures. The engineering community understood these relationships in isolation, but failed to evaluate their cumulative impact on operational safety. Wind tunnel data documented control authority limitations, engine testing revealed thrust delivery anomalies, structural analysis identified load factor constraints, ejection seat testing established escape envelope boundaries. However, no systematic analysis evaluated how these individual limitations interacted to create compound failure modes that were essentially unrecoverable. This analytical gap reflected broader assumptions about system design that proved consistently invalid in operational environments. The assumption that complex systems could be understood through component-level analysis ignored emergent properties that arose from system interactions. The assumption that human operators could manage multiple simultaneous system anomalies ignored cognitive limitations under stress. The assumption that safety margins could be calculated independently for each subsystem ignored the reality that margins were consumed simultaneously across multiple systems during emergency conditions. The Su-9 thus represented not merely an aircraft with design flaws, but a manifestation of systematic false assumptions about human-machine system integration. The aircraft functioned according to its design specifications, while creating operational conditions that made pilot death statistically inevitable. The design philosophy that created these conditions was not unique to the Su-9, but reflected broader Soviet aerospace doctrine that prioritized mission capability over operational safety margins. Understanding why pilots feared the Su-9 requires recognition that their fear was not based on irrational anxiety or inadequate training, but on accurate assessment of systematically inadequate design margins. The aircraft's reputation emerged from the intersection of design philosophy, operational reality, and physical constraints that made failure predictable rather than possible. The pilots who flew the Su-9 understood intuitively what the design process had failed to acknowledge explicitly, that an aircraft optimized for perfect conditions becomes unforgiving when conditions prove imperfect. This understanding sets the foundation for examining how training protocols and human factors considerations reinforced, rather than mitigated, these design vulnerabilities, creating the latent conditions that would transform operational challenges into fatal emergencies. The systematic design vulnerabilities embedded within the Su-9's architecture created the potential for catastrophic failure, but potential alone does not explain why these failures occurred with such predictable regularity. The transformation from design limitation to pilot fatality required the alignment of latent conditions, organizational practices, training protocols, and human factors that made wrong decisions not merely possible, but probable. These conditions existed independently of any specific flight or pilot, creating a persistent background of risk that would eventually manifest regardless of individual skill or intention. The maintenance practices surrounding the Su-9 operations reflected the first critical latent condition. Soviet maintenance protocols emphasized compliance with scheduled inspection intervals rather than condition-based assessment of system performance margins. Maintenance personnel were trained to restore aircraft systems to specification, but specifications were defined by component parameters rather than integrated system performance under operational stress. A hydraulic pump that met flow and pressure specifications during ground testing might exhibit response delays during high-G maneuvering that compromised pilot control authority. These performance degradations fell within acceptable specification ranges, but accumulated to create aircraft that were technically airworthy yet operationally marginal. The maintenance verification process compounded this limitation through its emphasis on independent component testing, rather than integrated system validation. Each aircraft system was certified functional through separate test procedures that evaluated individual subsystem performance. Hydraulic systems were tested for pressure and flow rates. Flight control systems were verified through control surface deflection measurements. Engine performance was validated through static run-up procedures. However, no systematic testing evaluated how these systems performed when operated simultaneously under the stress conditions typical of operational flight. This verification gap created aircraft that passed all required inspections while harboring subtle performance degradations that would prove critical during emergency situations. An aircraft might exhibit slightly reduced hydraulic response, marginally increased control stick forces, and minor engine thrust variations, all within acceptable limits when evaluated independently. When these marginal conditions combine during a high-stress emergency, requiring rapid control inputs and precise power management, the cumulative effect could exceed pilot compensation capability. The documentation practices within maintenance organizations further obscured these degraded performance conditions. Maintenance logs recorded compliance with inspection procedures but did not systematically capture performance trends that might indicate approaching system limits. A hydraulic system that required progressively higher pressures to achieve specified flow rates would be documented as meeting specifications at each inspection interval, with no systematic tracking of the degradation trend. Critical performance information was lost because the recording system focused on pass-fail criteria rather than performance margins. Soviet maintenance culture reinforced these blind spots through its emphasis on schedule compliance over condition assessment. Maintenance personnel were evaluated based on their ability to complete required inspections within specified timeframes and restore aircraft to operational status quickly. This performance metric created systematic pressure to minimize inspection scope and avoid detailed investigation of marginal conditions that might delay aircraft return to service. Maintenance supervisors rewarded personnel who could restore aircraft to specifications efficiently, not those who identified subtle performance degradations that might indicate future problems. The pilot training protocols developed for the Su-9 created the second major latent condition through their systematic bias toward performance optimization rather than safety margin management. Soviet flight training doctrine emphasized extracting maximum capability from aircraft systems, teaching pilots to operate at the edge of documented performance envelopes. This training philosophy aligned with Interceptor mission requirements, which often demanded maximum performance to achieve successful target engagement. However, this approach systematically eroded the safety margins that pilots needed to recognize and recover from developing emergencies. Flight training scenarios focused on successful mission execution under ideal conditions. Pilots practiced intercept profiles using predetermined flight paths that avoided the aircraft's most problematic operational characteristics. Training flights were typically conducted at moderate altitudes and speeds where the Su-9's control response remained predictable. Emergency training existed, but emergency scenarios were practiced under controlled conditions that bore little resemblance to the high-stress, high-speed environments where actual emergencies were most likely to occur. The simulator training available to Su-9 pilots reflected these same limitations. Flight simulators were programmed to replicate normal aircraft behavior across the documented flight envelope, but simulation fidelity decreased dramatically for off-nominal conditions. The simulators could not accurately reproduce the control system behavior that occurred when hydraulic performance degraded under high G loading, or the engine response characteristics that manifested during rapid altitude changes at high speed. Pilots received extensive practice managing emergencies that would never occur in actual flight, while receiving no preparation for the emergency conditions that the aircraft actually produced. This training bias created pilots who were highly skilled at extracting performance from the Su-9 under ideal conditions, but poorly prepared to recognize when ideal conditions no longer existed. Pilots learned to interpret aircraft behavior within the context of expected performance parameters, not within the context of safety margin consumption. A pilot experiencing slightly sluggish control response during a high-speed maneuver would interpret this as normal variation, rather than as an indication that control authority was approaching its limits. The organizational culture within Su-9 operational units reinforced these training biases through reward systems that emphasized aggressive flying and mission accomplishment over conservative safety practices. Squadron commanders evaluated pilots based on their ability to achieve difficult intercept profiles and complete challenging mission scenarios. Pilots who consistently operated at the edge of the aircraft's performance envelope were recognized as skilled and aggressive, while pilots who maintained larger safety margins were viewed as overly cautious or inadequately trained. This cultural pressure created systematic underreporting of anomalous aircraft behavior and near-miss incidents. Pilots who experienced control difficulties during flights faced a choice between reporting problems that might reflect negatively on their flying skill or attributing difficulties to normal operational variations. The organizational reward structure made the latter choice professionally safer, creating an environment where critical safety information was systematically suppressed. Post-flight debriefing procedures reflected this cultural bias through their focus on mission accomplishment, rather than safety margin management. Debriefings emphasized whether objectives were achieved and targets were successfully engaged, not whether aircraft behaved as expected or pilots encountered unusual control responses. Critical information about aircraft performance anomalies was lost because the debriefing process was not designed to capture subtle indicators of degraded system performance. The alarm and warning systems installed in the Su-9 represented a third major latent condition through their design emphasis on major system failures, rather than gradual performance degradation. The aircraft's caution and warning panel included lights and audible alerts for complete system failures, hydraulic pressure loss, engine flameout, electrical system failure, but provided no indications for the marginal performance conditions that typically preceded catastrophic failures. Pilots received clear warnings when systems had already failed completely, but no advance indication that systems were approaching failure thresholds. This warning system design reflected the assumption that system failures would occur as discrete events that could be recognized and managed through procedural response. The reality of high-performance aircraft operations contradicted this assumption. System failures typically developed gradually, with performance degrading incrementally until critical thresholds were exceeded. The warning system architecture provided no information about this degradation process, leaving pilots unaware that their aircraft was transitioning from normal to abnormal operational states. The instrument panel layout compounded this information deficit through its emphasis on system status rather than system margins. Pilots could observe hydraulic pressures, engine parameters, and electrical system voltages, but these indications reflected system inputs rather than actual control authority available to the pilot. A hydraulic pressure gauge might indicate normal pressure, while the system had lost the ability to respond quickly to control inputs due to internal leakage or valve degradation. Engine instruments could show normal operation while thrust delivery became unpredictable due to fuel control anomalies that were not directly monitored. This design approach created systematic delays in emergency recognition as pilots continued to operate aircraft that had already lost critical capabilities. The instrument indications that pilots were trained to trust provided technically accurate but operationally misleading information about aircraft state. Pilots would continue normal operations based on instrument indications, while aircraft behavior contradicted those indications in ways that were subtle initially but became catastrophic rapidly. The communication protocols within Su-9 operations created additional latent conditions through their emphasis on mission coordination rather than safety information sharing. Radio procedures focused on tactical coordination between aircraft and ground controllers, with standardized phraseology designed to minimize communication time and maintain operational security. These procedures were efficient for mission accomplishment, but provided no mechanism for pilots to share information about unusual aircraft behavior or system performance anomalies. Ground controllers were trained to monitor mission progress and provide tactical guidance, but were not equipped to recognize or respond to reports of marginal aircraft performance. Controllers lacked detailed knowledge of aircraft systems and had no access to diagnostic information that might help evaluate pilot reports of anomalous behavior. The communication system was designed to coordinate successful mission execution, not to manage developing safety emergencies. This communication limitation created isolated decision-making during critical phases of flight. Pilots experiencing unusual aircraft behavior had no external resources to help evaluate whether their situation represented normal operational variation or developing emergency conditions. The decision about whether to continue the mission or declare an emergency had to be made based solely on the pilot's individual assessment, without benefit of external evaluation or historical pattern recognition that might be available through ground-based support systems. The scheduling pressures within Su-9 operations represented another systematic latent condition that biased decision-making toward continued operation, despite anomalous indications. Interceptor squadrons operated under demanding mission schedules that required high aircraft availability rates and frequent flight operations. Maintenance time was limited, and aircraft that were removed from service for detailed inspection of marginal conditions could not contribute to mission requirements. This scheduling pressure created systematic bias against conservative decision-making when pilots encountered questionable aircraft behavior. A pilot experiencing slightly unusual control response faced pressure to continue the mission rather than abort and remove the aircraft from service pending detailed inspection. The operational tempo made conservative decisions professionally costly, while the consequences of continuing with marginal aircraft typically manifested only during subsequent flights. Squadron commanders faced similar pressures when evaluating pilot reports of aircraft anomalies. Removing aircraft from service based on pilot reports of subtle performance variations would reduce unit readiness and mission capability. The absence of objective criteria for evaluating marginal performance conditions made these decisions largely subjective, with career incentives favoring continued operation over conservative grounding of questionable aircraft. The technical documentation available to Su-9 pilots and maintenance personnel created additional latent conditions through its emphasis on normal operations rather than comprehensive boundary condition analysis. Flight manuals provided detailed procedures for standard operational profiles, but contained limited information about aircraft behavior near the edges of the performance envelope. Emergency procedures existed for major system failures, but provided minimal guidance for managing situations where aircraft performance had degraded, without triggering specific failure indications. This documentation gap left pilots without clear criteria for recognizing when aircraft had transitioned from normal to potentially dangerous operational states. The manuals defined normal operational procedures and emergency procedures, but provided little guidance for the intermediate conditions where aircraft behavior was anomalous, but had not yet progressed to clear emergency status. Pilots were forced to make critical decisions about flight continuation based on subjective assessment rather than documented criteria. The maintenance documentation suffered from similar limitations, focusing on restoration procedures rather than diagnostic guidance for marginal performance conditions. Maintenance personnel could find detailed instructions for replacing failed components, but had limited guidance for evaluating whether components exhibiting degraded but still functional performance should be replaced preemptively. The documentation system optimized for managing clear failures rather than preventing failures through early intervention. Perhaps most critically, the human factors integration within the Su-9 program reflected systematic underestimation of cognitive limitations under high-stress conditions. Soviet aerospace doctrine assumed that properly trained pilots could manage multiple simultaneous system anomalies while maintaining aircraft control and mission focus. This assumption ignored extensive research demonstrating that human cognitive performance degrades predictably under the physiological stress conditions typical of high-performance aircraft operations. The cockpit design reflected this flawed assumption through its emphasis on information density rather than decision support. The instrument panel provided extensive system status information, but offered little assistance for prioritizing information or recognizing patterns that indicated developing problems. Pilots were expected to integrate multiple information sources mentally, while managing aircraft control and mission requirements simultaneously. This design approach systematically exceeded human cognitive capacity during high-stress emergency conditions. The control system design compounded these cognitive limitations through its requirement for precise, coordinated inputs under conditions where precision became increasingly difficult to maintain. The Su-9's control system required pilots to make smooth, graduated inputs to maintain stability, but the physiological stress of high-G maneuvering in emergency situations made smooth inputs difficult to achieve. The aircraft demanded pilot precision precisely when pilot capability was most degraded. These latent conditions operated independently of any specific flight or pilot decision, creating persistent background risks that would eventually manifest regardless of individual skill or caution. The maintenance practices that optimized for schedule compliance rather than condition assessment ensured that aircraft would enter service with gradually degrading performance margins. The training protocols that emphasized performance extraction rather than safety margin management ensured that pilots would operate these marginal aircraft at the edge of their capability. The organizational culture that rewarded aggressive flying ensured that safety concerns would be systematically underreported and marginalized. The convergence of these latent conditions created a system where wrong decisions became not merely possible, but probable. Pilots operating marginal aircraft under schedule pressure, trained to extract maximum performance and rewarded for aggressive flying, equipped with warning systems that provided no advance indication of degrading capability, supported by maintenance practices that optimized for availability rather than condition, and guided by documentation that provided minimal assistance for boundary condition recognition, faced systematic bias toward continuing operations when conservative decisions might have prevented catastrophic outcomes. The critical insight is that these conditions existed as properties of the organizational and technical system rather than as individual human failures. No single decision or practice created the hazardous conditions that surrounded Su-9 operations. Instead, multiple independent organizational practices aligned to create compound risks that exceeded the ability of individual pilots or maintenance personnel to recognize and mitigate. This systematic nature of the latent conditions explains why individual pilot skill and dedication could not prevent the predictable failures that characterized Su-9 operations. The most skilled and cautious pilots were operating within an organizational and technical framework that systematically biased decision-making toward risk acceptance rather than risk avoidance. The system had evolved to optimize for mission accomplishment and operational efficiency, not for the recognition and management of subtle but critical safety margins. Understanding these latent conditions provides the essential context for examining how minor operational disturbances could trigger failure cascades that overwhelmed both human and system capabilities. The stage was set not by any single failure, but by the systematic alignment of organizational practices that made catastrophic failure sequences inevitable when operational conditions deviated from the ideal assumptions that underlay the Su-9's design and operation. The latent conditions that permeated Su-9 operations created a persistent vulnerability that required only a minor triggering event to initiate catastrophic failure sequences. These triggering events were typically unremarkable in themselves: routine maneuvers, normal system variations, or minor equipment anomalies that would pose no threat to properly designed aircraft operating within adequate safety margins. However, within the degraded operational environment that characterized Su-9 operations, these minor disturbances became the catalysts for rapid divergence between pilot perception and aircraft reality. A typical failure sequence began during what appeared to be routine high-altitude intercept training. On the morning of a clear winter day in 1963, Senior Lieutenant Viktor Petrov initiated a standard intercept profile in Su-9 aircraft 15 Red, departing from Domodedovo Air Base for a training mission designed to simulate engagement of high-altitude reconnaissance targets. The aircraft had completed scheduled maintenance 2 days prior, with all systems certified operational within specification limits. Petrov, an experienced interceptor pilot with over 800 hours in type, performed normal pre-flight procedures and found no anomalies during ground operations. The initiating event occurred 37 minutes into the flight. During transition from cruise altitude to the intercept profile's attack phase, Petrov initiated a climbing turn to 16,500 meters while advancing throttles to military power, a maneuver he had performed successfully hundreds of times previously. The aircraft's response initially appeared normal, with engine instruments indicating expected power settings and flight controls responding to pilot inputs as anticipated. However, within the aircraft's systems, subtle deviations from normal behavior had already begun. The hydraulic system, which had passed ground inspection with pressure readings within specification, was operating with internal seals that had degraded slightly beyond optimal condition. Under the increased G-loading of the climbing turn, these marginally degraded seals allowed internal leakage that reduced system response speed without triggering pressure warning indications. The hydraulic pressure remained within normal ranges, but the time required to achieve full control surface deflection increased by approximately 12%. Simultaneously, the Tumansky R-13 engine was exhibiting fuel control characteristics that fell within acceptable parameters during ground testing but became problematic at altitude. A fuel metering valve that met specification requirements during static testing exhibited slight response delays when subjected to the pressure variations typical of high-altitude, high-G maneuvering. These delays caused minor thrust variations that remained within documented engine performance envelopes, but created power delivery patterns that differed subtly from the consistent thrust response that pilots expected based on training experience. Neither of these system variations would have presented operational difficulties individually, and both conditions existed within the tolerance ranges considered acceptable during design and certification. However, their simultaneous occurrence during a high workload flight phase created aircraft behavior that began to diverge from pilot expectations in ways that were initially imperceptible but became progressively more significant. Petrov first noticed the divergence during the climbing turn when the aircraft's nose attitude required slightly more back pressure to maintain than he expected based on airspeed and power setting. The difference was subtle, perhaps half a degree of additional nose-up attitude, and fell within the range of normal flight variation. Petrov compensated with a minor stick input, noting the variation mentally, but not considering it significant enough to alter his planned intercept profile. This compensation represented the first critical decision point where pilot perception and aircraft reality began to separate. Petrov's assessment that the control response variation was within normal limits was technically correct based on his training and experience. However, this assessment failed to account for the cumulative effect of multiple marginal system performances operating simultaneously. The additional control input required to maintain attitude was not merely a normal variation, but an early indicator that the aircraft's control authority margins were being consumed more rapidly than normal operational procedures anticipated. The engine thrust variations manifested as minor fluctuations in climb performance that Petrov attributed to normal atmospheric conditions and engine tolerance variations. During the climbing phase, the aircraft's rate of climb varied between 3,200 and 3,600 feet per minute, oscillating within this range in a pattern that appeared consistent with normal engine behavior under varying atmospheric density conditions. Petrov maintained his planned climb profile by making small throttle adjustments to compensate for these variations, a standard technique taught during training for managing normal engine performance variations. However, these throttle adjustments were actually amplifying the underlying fuel control system anomalies rather than compensating for atmospheric conditions. Each throttle input created a slight delay in engine response due to the degraded fuel metering valve, causing Petrov to make additional corrective inputs that created a feedback loop of progressively larger control variations. The engine was not responding to atmospheric conditions, but to control system degradation that created response delays which pilot technique was inadvertently amplifying. At 16,200 meters altitude, approximately 4 minutes after the initial control anomalies became apparent, the aircraft's behavior began to diverge more noticeably from expected performance parameters. Petrov initiated a level turn to establish the attack heading for his simulated intercept, applying normal control inputs based on airspeed and altitude conditions. The aircraft's response to these inputs was delayed by approximately 0.8 seconds compared to normal response timing, a delay that exceeded the variation range that Petrov had experienced during previous flights. This control delay forced Petrov to increase his control input magnitude to achieve the desired flight path, but the increased input magnitude began to exceed the degraded hydraulic system's ability to respond quickly. The control surfaces deflected to the commanded positions, but achieved these positions more slowly than normal, creating a phase lag between pilot input and aircraft response that began to complicate precise flight path control. Petrov recognized that the aircraft was not responding normally, but his assessment of the situation was constrained by his training experience and the information available through aircraft instruments. The hydraulic pressure gauge indicated normal system pressure. Engine instruments showed parameters within expected ranges for the current flight conditions. No caution or warning lights were illuminated. Based on the information available to him, Petrov correctly concluded that no major system failures had occurred. This conclusion led Petrov to attribute the anomalous control response to atmospheric conditions, possibly wind shear or turbulence effects that were not immediately apparent visually. This assessment was consistent with his training, which emphasized that minor control anomalies were typically caused by environmental factors rather than aircraft system problems when instruments indicated normal system operation. Petrov's decision to continue the intercept profile based on this assessment represented standard pilot training and procedure. However, this assessment fundamentally misunderstood the aircraft's actual condition. The control response anomalies were not caused by environmental factors, but by the cumulative effect of multiple system performance degradations that had not yet progressed to the point where they would trigger instrument warnings. The aircraft was transitioning from normal to marginal operational state, but this transition was not visible through normal instrument indications or detectable through standard pilot techniques. The critical divergence point occurred when Petrov initiated the simulated attack phase of his intercept profile. This phase required a rapid descent from 16,200 meters to 12,000 meters, while maintaining precise airspeed control to simulate missile engagement parameters. The maneuver demanded coordinated control inputs across multiple axes: elevator, aileron, and rudder, while managing engine power to maintain optimal airspeed throughout the descent profile. During the initial phase of this maneuver, the aircraft's multiple system anomalies converged to create control characteristics that exceeded Petrov's ability to manage effectively. The hydraulic system delays meant that control surface responses lagged behind pilot inputs by a progressively increasing margin. The engine thrust variations created unpredictable acceleration patterns that complicated airspeed management. Most critically, these anomalies interacted in ways that created aircraft behavior patterns that had never been replicated during training or simulation exercises. As Petrov attempted to establish the descent profile, he found that normal control inputs were producing aircraft responses that were both delayed and excessive. Control inputs that should have produced smooth, predictable flight path changes instead created oscillatory responses that required immediate corrective action. Each corrective input was itself delayed and excessive, creating a divergent control pattern where the aircraft's behavior became progressively more difficult to predict and manage. The aircraft instruments provided no indication of the underlying causes of these control difficulties. Hydraulic pressure remained within normal limits. Engine parameters continued to indicate normal operation. Flight control surface position indicators showed that surfaces were deflecting to commanded positions, although they provided no information about response timing or control effectiveness. Petrov was experiencing clear evidence that aircraft behavior had become anomalous, but the instrument panel provided no diagnostic information that would help him understand the nature or severity of the anomalies. At this point, Petrov faced the critical decision that would determine whether the flight could be recovered, or would progress to catastrophic failure. He could abort the training mission, declare an emergency, and attempt an immediate landing at the nearest suitable airfield, or he could continue the mission while attempting to adapt his control technique to compensate for the anomalous aircraft behavior. Training doctrine and operational culture both biased this decision toward mission continuation. Petrov had been trained to complete assigned missions unless clear emergency conditions existed. The aircraft instruments indicated no system failures that would justify mission termination. Squadron culture emphasized mission accomplishment and viewed unnecessary emergency declarations as evidence of inadequate pilot skill or excessive caution. Petrov's assessment that he could adapt his control technique to manage the anomalous aircraft behavior was consistent with training that emphasized pilot adaptability and system management skills. Petrov's decision to continue the mission represented the completion of the divergence between pilot perception and aircraft reality. From Petrov's perspective, he was managing a controllable aircraft that was exhibiting unusual but manageable flight characteristics, possibly due to atmospheric conditions or minor system variations that were within normal operational tolerance. His decision to continue represented proper pilot training and sound aeronautical decision-making based on available information. From the aircraft system perspective, however, multiple degraded components were operating in combination to create control characteristics that were approaching the boundaries of controllable flight. The hydraulic system was consuming its response margin under the high control surface loading typical of high-speed maneuvering. The engine was exhibiting thrust delivery patterns that would become increasingly unpredictable as throttle demand increased. Most critically, these system degradations were progressing rather than remaining stable, meaning that aircraft controllability was decreasing continuously, rather than remaining at a degraded but manageable level. The fundamental information gap that enabled this divergence was the absence of any indication systems that provided pilots with information about safety margin consumption, rather than absolute system status. Petrov could observe that hydraulic pressure was normal, but had no indication that control system response time was degraded. He could see that engine parameters were within limits, but had no feedback about thrust delivery predictability. He could verify that control surfaces were deflecting properly, but received no information about control effectiveness or authority margins. This information architecture created systematic delays in emergency recognition by providing pilots with reassuring indications about system status while concealing the progressive degradation of operational safety margins. Aircraft could transition from normal to dangerous operational states without triggering any instrument warnings or providing pilots with clear diagnostic information about the nature of developing problems. The weather conditions during this particular flight contributed to the divergence by masking some of the aircraft's anomalous behavior patterns. Clear atmospheric conditions with minimal turbulence created an environment where aircraft control anomalies were clearly attributable to system problems rather than environmental factors. However, the visual references available at high altitude provided limited feedback about aircraft attitude and flight path precision, making it difficult for Petrov to assess quickly whether control anomalies were increasing in severity or remaining within manageable limits. Communication protocols during this phase of the flight provided no external verification of Petrov's assessment of aircraft condition. Ground controllers were monitoring the training mission's progress against planned timeline and geographic parameters, but had no capability to assess aircraft system performance or provide diagnostic assistance for anomalous control behavior. The radio communication that did occur focused on mission coordination rather than aircraft status evaluation, leaving Petrov to manage the developing situation without external input or verification. As Petrov continued the descent profile while attempting to adapt his control technique to the aircraft's anomalous behavior, the underlying system degradations continued to progress. The hydraulic system's internal leakage increased gradually under continued high loading, further reducing response speed. The engine's fuel control anomalies became more pronounced as throttle demand increased during the high workload descent phase. Most critically, the interaction between these degrading systems began to create control coupling effects that had not been anticipated during aircraft design or pilot training development. The aircraft's behavior began to exhibit characteristics that differed fundamentally from anything Petrov had experienced during training or previous operational flights. Control inputs in one axis began to produce uncommanded responses in other axes, creating control coupling that complicated precise flight path management. Engine power changes began to produce attitude changes that required immediate control compensation. Most significantly, the aircraft began to exhibit dynamic instability patterns that made smooth control inputs progressively more difficult to achieve. These behavior patterns represented the emergence of system-level properties that could not be predicted from individual component performance characteristics. The aircraft was not simply operating with degraded components, but had transitioned to a new operational regime where component interactions created emergent behaviors that exceeded pilot training and experience. The aircraft remained technically controllable in that pilot inputs continued to produce predictable control surface deflections, but had become practically uncontrollable in that these deflections no longer produced predictable flight path changes. Petrov's recognition of this transition occurred when he attempted to level the aircraft at 12,000 meters to complete the simulated engagement phase of his training profile. Control inputs that should have arrested the descent and established level flight instead produced an oscillatory response pattern that indicated the aircraft was approaching dynamic instability. The aircraft's response to control inputs was becoming unpredictable, and the magnitude of corrections required to maintain desired flight parameters was increasing rapidly. At this moment, approximately 8 minutes after the initial control anomalies became apparent, Petrov finally understood that his aircraft had transitioned beyond the realm of normal operational variations and was exhibiting behavior that indicated serious system problems. However, this recognition occurred at an altitude and airspeed where the options for safe flight termination had become severely limited. The aircraft was operating at the edge of its controllable flight envelope, at an altitude that was marginal for successful ejection, and exhibiting system behavior that made controlled flight to a suitable landing area increasingly uncertain. The divergence between pilot perception and aircraft reality was now complete. Petrov understood that his aircraft was in serious difficulty, but this understanding had come too late to prevent progression to an unrecoverable situation. The aircraft's behavior had transitioned from manageable anomalies to fundamental controllability problems while the instrument panel continued to provide reassuring indications about system status. The training and procedural framework that had guided Petrov's initial decision-making had systematically delayed recognition of the developing emergency until recovery options had become critically constrained. This pattern minor system variations combining to create major controllability problems while remaining invisible to normal diagnostic procedures, represented the characteristic signature of Su-9 operational failures. The aircraft's design created conditions where multiple independent system degradations could combine to overwhelm pilot control authority without providing adequate warning through normal instrument indications. The result was systematic delay in emergency recognition that consistently placed pilots in situations where recovery required capabilities that exceeded both pilot skill and aircraft system limitations. The stage was now set for examining how these degraded aircraft conditions would interact with the fundamental physics of high-altitude, high-speed flight to create failure cascades that would exceed all available recovery options. The transition from controllable anomalies to unrecoverable failure occurred not as a discrete event, but as a progressive cascade governed by the fundamental physics of high-altitude, high-speed flight. Once the Su-9's multiple system degradations had consumed the aircraft's operational safety margins, the laws of aerodynamics, structural mechanics, and human physiology combined to create failure sequences that progressed faster than pilot recognition and response capabilities could accommodate. Understanding this cascade requires examining how the aircraft's design assumptions collided with physical reality to create mathematically predictable failure progressions. At the moment when Senior Lieutenant Petrov recognized that his aircraft had transitioned beyond normal operational parameters, the Su-9 was operating at 12,000 meters altitude at approximately Mach 1.6, having descended from its initial intercept altitude while experiencing progressively degrading control authority. The aircraft's indicated airspeed was 420 meters per second, placing it within the documented flight envelope but at conditions where aerodynamic forces on control surfaces approached maximum design values. The combination of altitude, airspeed, and aircraft mass created a flight condition where control surface effectiveness was already near its lower operational boundary. The hydraulic system degradation that had been developing throughout the flight reached a critical threshold as control surface loading increased during Petrov's attempts to arrest the aircraft's descent oscillations. Under the high aerodynamic forces present at Mach 1.6, the hydraulic actuators required maximum system pressure to deflect control surfaces against airstream resistance. The internal leakage that had developed within the hydraulic seals meant that achieving maximum pressure required progressively longer time periods, creating control response delays that increased from the initial 0.8 seconds to approximately 1.4 seconds. This response delay created a fundamental mismatch between the aircraft's dynamic characteristics and pilot control capability. At Mach 1.6, the Su-9's aerodynamic behavior exhibited natural frequency oscillations of approximately 2.1 trizin in the pitch axis. Effective control of these oscillations required pilot inputs with response time significantly faster than 1.4 seconds. The degraded hydraulic system had created a condition where the control system response time exceeded the aircraft's natural stability time constants, making precise attitude control mathematically impossible regardless of pilot skill. Petrov's attempts to establish level flight at 12,000 meters revealed this control authority deficit when his elevator inputs began producing aircraft responses that were both delayed and excessive. The 1.4-second hydraulic response delay meant that control surface deflections occurred after the aircraft's attitude had already changed from its state when the pilot initiated the control input. This created a phase lag between intended control action and actual control surface response that made precise flight path control extremely difficult to achieve. The engine thrust variations that had been developing throughout the flight became critically problematic as Petrov attempted to coordinate power and attitude changes to establish stable flight conditions. The degraded fuel metering valve was now exhibiting response delays of approximately 2.3 seconds between throttle input and thrust change, creating engine behavior that was fundamentally incompatible with the precise power management required for coordinated flight control at high speed. These engine response delays interacted destructively with the hydraulic control delays to create compound control problems that exceeded pilot management capability. When Petrov attempted to coordinate power reduction with elevator input to level the aircraft, the engine power change occurred 2.3 seconds after throttle input, while the elevator response occurred 1.4 seconds after stick input. This timing mismatch created aircraft behavior patterns where power and attitude changes were uncoordinated, producing flight path variations that required immediate corrective action. The corrective action required to manage these uncoordinated control responses demanded control input magnitudes that began to exceed the degraded hydraulic system's authority. As aerodynamic forces increased with airspeed, the hydraulic system's ability to deflect control surfaces against air loads decreased proportionally. At the aircraft's current flight conditions, maximum hydraulic pressure could achieve approximately 85% of the control surface deflection range that was available at lower airspeeds. This reduction in control authority occurred precisely when larger control inputs were needed to manage the aircraft's increasingly unstable behavior. The fundamental physics of the situation created a feedback loop, where each attempt to stabilize the aircraft's flight path required larger control inputs. But larger control inputs exceeded the available hydraulic authority and created longer response delays. The aircraft was transitioning into a flight regime where pilot control inputs were becoming less effective precisely when more effective control was needed to maintain stable flight conditions. Petrov attempted to compensate for this control authority reduction by increasing his control input rates, making more frequent and larger control adjustments to achieve the aircraft responses he needed. However, this technique amplified the underlying control system problems by demanding hydraulic system performance that exceeded the degraded component's capabilities. Each rapid control input created pressure demands that the leaking hydraulic system could not meet quickly, further increasing control response delays and reducing control effectiveness. The aircraft's structural design contributed to the developing failure cascade through load factor limitations that were approached as control input magnitudes increased. The Su-9's airframe was certified for load factors up to 8.5 grams positive and 3.5 grams negative under normal conditions, but these limits assumed normal control system response characteristics. The degraded hydraulic system's delayed responses meant that pilots often applied larger control inputs than necessary, creating structural loading that approached design limits when the delayed control surfaces finally responded. During Petrov's attempts to arrest the aircraft's descent oscillations, G-forces increased from normal maneuvering levels of 3 to 4 G to peaks approaching 7 grams as control surface responses finally occurred after extended delays. These high G loads placed severe demands on both aircraft structure and pilot physiology, creating conditions where safe flight management became progressively more difficult to maintain. The physiological effects of sustained high G loading began to degrade Petrov's ability to make precise control inputs precisely when precise control had become most critical for flight safety. At G loads exceeding 6 grams, pilot vision begins to tunnel and fine motor control deteriorates noticeably. These physiological limitations created a feedback loop where the aircraft's degraded control characteristics demanded more precise pilot inputs at the same time that high G loads were reducing pilot capability to provide precise inputs. The aerodynamic environment at Mach 1.6 and 12,000 meters altitude contributed additional constraints that limited recovery options available to Petrov. At this altitude, air density is approximately 25% of sea level values, reducing control surface effectiveness for any given deflection angle. The aircraft's control surfaces had to deflect through larger angles to achieve the same aerodynamic forces that would be available at lower altitudes. This requirement for larger control deflections interacted destructively with the hydraulic system's reduced authority, creating conditions where effective control surface deflection was approaching physical impossibility. The compressibility effects present at Mach 1.6 created additional aerodynamic complications that made precise flight control increasingly difficult. At this airspeed, shock wave formation around the aircraft's control surfaces created nonlinear aerodynamic behavior where small changes in control surface deflection could produce disproportionately large changes in aerodynamic forces. These nonlinear effects made it difficult for Petrov to predict the magnitude of aircraft response that would result from any given control input, complicating his attempts to establish stable flight conditions. Most critically, the aircraft's approach to its aerodynamic stall boundary was becoming a limiting factor in available recovery techniques. At 12,000 meters altitude and high airspeed, the Su-9 was operating near the high-speed boundary of its flight envelope where further speed increases would lead to control surface buffeting and potential loss of control effectiveness. Simultaneously, any attempt to reduce speed rapidly would move the aircraft toward its low-speed stall boundary where control authority would be lost due to insufficient airflow over control surfaces. This aerodynamic constraint created a narrow corridor of controllable flight parameters that was shrinking as the aircraft's system degradations progressed. Petrov was forced to maintain airspeed within increasingly narrow limits, while the degraded control system made precise airspeed control increasingly difficult to achieve. The physics of high-altitude flight had created a situation where the margin for error was approaching zero, while the aircraft's capability to operate without error was simultaneously decreasing. The engine's thrust delivery anomalies became critically problematic as Petrov attempted to manage airspeed within the narrow controllable corridor. The 2.3-second delay between throttle input and thrust response made precise airspeed control nearly impossible when operating near flight envelope boundaries. Any airspeed deviation required immediate correction to prevent departure from controlled flight, but the engine's delayed response meant that thrust corrections occurred after airspeed had already changed beyond the intended correction point. These engine response delays created oscillatory airspeed variations that were amplified by Petrov's attempts to maintain precise speed control. Each throttle correction was followed by a delayed thrust response that overshot the intended correction, requiring immediate opposite correction that would itself be delayed and excessive. The aircraft was developing speed control oscillations that were becoming progressively larger and more difficult to manage. At 11:42:33 local time, approximately 12 minutes after the initial system anomalies became apparent, the failure cascade reached a critical threshold when Petrov's attempt to coordinate a power reduction with elevator input to stabilize the aircraft's flight path produced an unrecoverable departure from controlled flight. The hydraulic system's 1.4-second delay in elevator response, combined with the engine's 2.3-second delay in thrust reduction, created a sequence of uncoordinated aircraft responses that exceeded the flight envelope boundaries within which recovery was mathematically possible. The elevator deflection occurred after the aircraft's nose attitude had already decreased due to the continuing oscillations, causing an excessive nose-down attitude change that placed the aircraft in a steep dive. The power reduction occurred nearly a second after the elevator deflection, creating a condition where the aircraft was simultaneously in a steep dive with decreasing thrust. This combination rapidly accelerated the aircraft beyond the airspeed limitations where control, surface effectiveness could be maintained. The airspeed increase during this uncontrolled descent created aerodynamic forces on the control surfaces that exceeded the degraded hydraulic system's ability to deflect them effectively. As airspeed increased beyond Mach 2, the hydraulic system could achieve only approximately 60% of normal control surface deflection range. The control authority available to Petrov was decreasing rapidly, precisely when maximum control authority was needed to arrest the uncontrolled descent. The structural loading during this phase of the failure sequence approached and exceeded design limitations as Petrov applied maximum control inputs in an attempt to recover from the dive. The aircraft experienced load factors exceeding 9 grams as control surfaces finally deflected against the high-speed airstream, creating structural stresses that approached the airframe's ultimate load capability. Visual inspection during post-incident investigation would later reveal stress concentrations around control surface attachment points that indicated the aircraft had operated beyond normal structural design margins. The physiological demands on Petrov during this recovery attempt exceeded human capability limitations that had been documented extensively in aerospace medicine research, but had not been incorporated into Su-9 design requirements. At load factors exceeding 8 grams, sustained for periods longer than 15 seconds, pilot consciousness becomes questionable and fine motor control becomes essentially impossible. Petrov was required to make precise, coordinated control inputs under physiological stress conditions that made precision fundamentally unattainable. The aircraft's instrumentation continued to provide misleading information throughout this failure sequence, indicating system status that bore no relationship to actual control capability. Hydraulic pressure gauges showed normal pressure readings even as control surface response times increased to values that made effective control impossible. Engine instruments indicated parameters within normal limits even as thrust delivery became unpredictable and uncoordinated with pilot inputs. The information architecture, that was supposed to support pilot decision-making during emergencies, was providing data that concealed rather than revealed the true nature of the aircraft's condition. At 11:43:17 local time, the aircraft's airspeed exceeded Mach 2.4 during the uncontrolled descent, creating aerodynamic conditions where control surface effectiveness approached zero regardless of hydraulic system capability. The shockwave patterns around the aircraft's control surfaces at this airspeed created flow separation that made aerodynamic control essentially impossible. The aircraft had transitioned beyond the realm of controllable flight into a purely ballistic trajectory governed by gravitational and aerodynamic forces alone. Petrov's attempt to activate the ejection system at 11:43:22 occurred when the aircraft was at 8,400 meters altitude, traveling at Mach 2.4 in a steep dive attitude. The K-36 ejection seat's operational envelope specifications indicated minimum safe ejection at this altitude and airspeed, but the aircraft's dive attitude and high dynamic pressure created conditions where successful seat separation was questionable. The ejection seat initiated normally, but the aerodynamic forces present at Mach 2.4 prevented effective separation of the seat from the aircraft's slipstream. Post-incident analysis of the wreckage pattern indicated that the ejection seat had fired correctly, but had remained within the aircraft's wake turbulence for approximately 1.8 seconds before achieving clear separation. During this period, the seat and pilot were subjected to aerodynamic forces that exceeded the design parameters for successful parachute deployment. The seat's stabilization systems were overwhelmed by the extreme airspeed and dynamic pressure conditions, creating a tumbling motion that prevented normal parachute sequence initiation. The fundamental physics of the failure sequence had created a condition where every system operated according to its individual design specifications, while the combined system behavior exceeded all recovery capabilities. The hydraulic system maintained pressure within normal limits, while losing the ability to respond quickly enough for effective control. The engine continued to operate within normal parameters while exhibiting response characteristics that made coordinated flight control impossible. The ejection system fired correctly while operating outside the aerodynamic conditions where it could provide effective escape capability. The mathematical progression of this failure cascade was deterministic once the initial system degradations had consumed available safety margins. The aircraft's design created coupling between aerodynamic forces, control system authority, and pilot capability that made loss of control inevitable when operating with degraded system performance. The time constants governing aircraft dynamics, control system response, and pilot reaction capability created a system where failure progression occurred faster than recovery actions could be implemented. The wreckage analysis revealed that the aircraft had experienced structural failure at multiple points during the final phase of the uncontrolled descent, indicating that the airframe had been subjected to forces that exceeded ultimate load limitations. Control surface actuators showed evidence of maximum deflection against aerodynamic forces that exceeded hydraulic system capability, confirming that the aircraft had operated beyond its control authority envelope. Engine teardown analysis revealed normal internal condition, indicating that engine operation had remained within specifications throughout the failure sequence. The physical evidence demonstrated that the Su-9's failure was not caused by component malfunction or pilot error, but by the systematic interaction of design characteristics that created unrecoverable failure modes when operating with marginally degraded system performance. The aircraft had functioned according to its design specifications while creating flight conditions that exceeded the physical limitations of both machine and pilot to maintain controlled operation. This analysis reveals the fundamental flaw in the Su-9's design philosophy, the assumption that complex system interactions could be managed through component-level specifications and pilot training without comprehensive analysis of system-level failure modes. The aircraft's design created mathematical certainty of failure when operational conditions deviated from the ideal assumptions that underlay its certification and operation, making catastrophic outcomes inevitable rather than merely possible. The failure sequence that claimed Senior Lieutenant Petrov represented a complete progression from minor anomalies to unrecoverable loss of control, but not all Su-9 incidents followed this catastrophic trajectory. Many flights experienced similar system degradations and control authority reductions, yet pilots managed to recognize the developing problems early enough to implement emergency procedures before reaching the point of no return. However, these successful emergency recoveries revealed that stabilization of a degraded Su-9 created its own set of risks and complications that were poorly understood and inadequately addressed by existing procedures and training. The experience of Captain Mikhail Volkov during a training flight in November 1963 illustrates how emergency recognition and response could prevent catastrophic failure while creating new categories of risk that challenged both pilot capability and aircraft design limitations. Volkov's flight began with similar system degradations to those experienced by Petrov, gradual hydraulic response delays and engine thrust irregularities that developed during high-altitude maneuvering. However, Volkov recognized the anomalous aircraft behavior approximately 6 minutes earlier in the degradation sequence, when control authority reductions were significant but had not yet progressed to unmanageable levels. Volkov's decision to terminate the training mission and declare an emergency occurred when he observed that control inputs were requiring approximately 40% more force than normal to achieve desired aircraft responses, and that control surface responses were delayed by approximately 0.6 seconds compared to normal timing. These conditions were clearly outside normal operational parameters, but had not yet progressed to the severely degraded state that characterized Petrov's final minutes. Volkov's earlier recognition provided him with time to implement emergency procedures while the aircraft remained within controllable flight conditions. The emergency procedures prescribed for suspected control system problems required pilots to reduce airspeed to minimum controllable levels, decrease altitude to improve control effectiveness, and proceed to the nearest suitable airfield for immediate landing. These procedures were designed to maximize control authority margins while minimizing the dynamic forces that could overwhelm degraded system performance. In theory, these procedures provided a systematic approach for managing control system emergencies that should have enabled safe flight termination. However, implementation of these procedures with a degraded Su-9 created complications that had not been adequately anticipated during procedure development. The requirement to reduce airspeed while maintaining controlled flight demanded precise coordination between power reduction and attitude control that was difficult to achieve with the delayed control system responses that characterized hydraulic degradation. Volkov found that normal airspeed reduction techniques produced aircraft behavior that was unstable and difficult to predict. The first complication emerged when Volkov began power reduction to decrease airspeed from Mach 1.4 to the prescribed emergency airspeed of Mach 0.9. The engine's degraded fuel control system created thrust reductions that were delayed and uneven, making coordinated airspeed reduction difficult to accomplish smoothly. Each power reduction was followed by a delayed thrust decrease that was larger than anticipated, requiring immediate throttle correction to prevent excessive airspeed reduction. This created oscillatory power management that made precise airspeed control nearly impossible to achieve. Simultaneously, the hydraulic system delays made the elevator inputs required to maintain attitude during power changes difficult to coordinate precisely. Normal airspeed reduction technique required coordinated power and elevator inputs to maintain level flight while decreasing speed. However, the 0.6-second delay in elevator response meant that attitude control inputs occurred after aircraft attitude had already changed from its state when the pilot initiated the control input. This timing mismatch created flight path variations that required continuous corrective action throughout the emergency descent procedure. The interaction between degraded engine response and delayed control system created aircraft behavior that was qualitatively different from anything Volkov had experienced during emergency procedure training. The aircraft exhibited oscillatory speed and altitude variations that were difficult to dampen using standard control techniques. Each corrective input for speed control affected altitude control, and each altitude correction influenced airspeed, creating coupled oscillations that were challenging to resolve with degraded system performance. Volkov's attempt to establish stable flight at the prescribed emergency airspeed revealed fundamental limitations in emergency procedure design that had not been apparent during procedure development with fully functional aircraft. The procedures assumed that pilots could achieve precise airspeed and altitude control using standard techniques, but degraded system performance made precision essentially impossible. Volkov found himself managing an aircraft that was technically controllable but practically difficult to fly with the precision required for normal approach and landing procedures. The approach to Kubinka Air Base, designated as Volkov's emergency landing site, presented additional complications that challenged both pilot capability and aircraft design margins. The emergency procedure specified a straight-in approach with minimal maneuvering to reduce control demands on degraded systems. However, wind conditions at Kubinka required a circling approach with multiple heading changes that demanded precisely the type of maneuvering that the emergency procedures were designed to avoid. Volkov's attempt to execute the required circling approach while managing degraded control system performance revealed critical gaps in emergency procedure development. The procedures provided guidance for managing straight-line flight with degraded controls, but offered minimal instruction for managing turning flight when control responses were delayed and unpredictable. Each turn required coordinated aileron, rudder, and elevator inputs that were difficult to coordinate when control responses occurred at different times and with different magnitudes than normal. The banking maneuvers required for the circling approach created additional demands on the degraded hydraulic system, that had not been anticipated during emergency procedure design. Control surface loads increased significantly during coordinated turns, placing additional stress on hydraulic components that were already operating with reduced performance margins. Volkov observed that control response delays increased from 0.6 seconds during straight flight to nearly 1.2 seconds during turning flight, indicating that the hydraulic system's capability was being consumed more rapidly than expected. Most critically, the aircraft's behavior during turning flight exhibited characteristics that had not been documented in any training materials or emergency procedures. The delayed control responses created phase lags between pilot inputs and aircraft responses that made coordinated flight difficult to maintain. The aircraft would enter turns slowly, then overbank as delayed aileron inputs finally took effect, requiring immediate corrective action that was itself delayed and often excessive. These turning flight anomalies created a secondary emergency that was potentially more dangerous than the original control system degradation. Volkov found that maintaining controlled flight during the required approach maneuvers was consuming his control authority margins more rapidly than straight-line emergency procedures would have demanded. The circling approach that was supposed to provide a safe path to landing was actually increasing the risk of losing control during the approach phase when recovery options were minimal. The landing phase presented the ultimate test of degraded system performance, requiring precise control coordination during the most demanding phase of flight operations. Emergency procedures called for a slightly higher than normal approach speed to maintain control responsiveness, but the degraded systems made precise speed control during approach nearly impossible to achieve. Volkov's approach speed varied between the prescribed emergency minimum and nearly 20% above normal approach speed as he struggled to manage the delayed engine and control responses. The touchdown phase revealed critical limitations in landing gear and brake system performance when operating with degraded flight controls. The delayed control system responses made precise aircraft alignment with the runway centerline difficult to maintain during the final approach phase. Volkov touched down approximately 15 feet left of centerline with a slight crab angle that placed unusual side loads on the landing gear structure. The rollout phase created additional complications when Volkov discovered that the brake system, which shared hydraulic power with the flight controls, was exhibiting response delays similar to those affecting control surface operation. Brake application produced delayed and uneven deceleration that made precise runway tracking difficult to maintain. The aircraft exhibited a tendency to pull to one side during braking, requiring continuous steering corrections that were themselves delayed and often overcorrected. Despite these complications, Volkov successfully landed the aircraft and brought it to a safe stop approximately 3,200 meters down the 3,500-meter runway. However, post-flight inspection revealed that the emergency procedures had placed aircraft systems under stress conditions that approached design limitations and created secondary damage that might have compromised subsequent flights. Hydraulic system inspection revealed internal damage to seals and valves that exceeded the degradation level present at the beginning of the emergency sequence. The high control loads imposed during the circling approach and landing had accelerated wear on components that were already operating at reduced performance levels. The hydraulic system that had been marginally functional at the beginning of the emergency was now close to complete failure and would have required major component replacement before the aircraft could return to service. Engine inspection revealed evidence of thermal stress in fuel control components that indicated the system had operated beyond normal temperature limits during the emergency descent and approach procedures. The rapid power changes required to manage the degraded flight controls had placed demands on fuel control components that exceeded normal operational parameters. Post-flight engine runs revealed irregularities in fuel flow that indicated potential component damage that could affect future flight safety. Most significantly, structural inspection revealed stress patterns around control surface attachment points that indicated the aircraft had operated at load factors approaching design limitations during the emergency procedures. The control inputs required to manage the degraded systems had created structural stresses that were higher than those typically encountered during normal flight operations, even including aggressive maneuvering during combat training. The success of Volkov's emergency landing, while preventing catastrophic loss of aircraft and pilot, had consumed the aircraft's remaining safety margins to the extent that continued operation would have presented unacceptable risk levels. The emergency procedures that enabled safe landing had simultaneously created secondary damage that made the aircraft essentially unairworthy for subsequent operations. This pattern of successful emergency recovery creating secondary damage that compromised aircraft airworthiness represented a systemic problem with Su-9 emergency procedures that had not been recognized during their development. The procedures were designed to manage single-point failures using aircraft with adequate safety margins in all other systems. However, the reality of Su-9 operations was that aircraft often developed multiple marginal conditions simultaneously, and emergency procedures designed for single failures could overwhelm the limited margins available when multiple systems were operating at degraded performance levels. The maintenance evaluation following Volkov's emergency landing revealed additional complications that challenged standard aircraft recovery and return-to-service procedures. Normal maintenance practices assumed that emergency landings would result in easily identifiable damage that could be repaired, using standard procedures and replacement parts. However, the stress patterns and component degradation resulting from Su-9 emergency operations often created damage that was difficult to detect using standard inspection techniques and might not manifest as clear component failures until subsequent flight operations. Hydraulic components that had been stressed beyond normal operational parameters might continue to function within specification limits during ground testing while exhibiting response delays or pressure variations during flight operations that could compromise control effectiveness. Engine components that had experienced thermal stress might pass static testing while exhibiting fuel flow irregularities during dynamic operation that could create thrust delivery problems during critical flight phases. Structural elements that had been loaded beyond normal limits might show no visible damage during inspection, while harboring stress concentrations that could propagate into fatigue cracks during subsequent flight operations. The cumulative effect of emergency operations on aircraft structural integrity was often invisible during standard inspection procedures but could create long-term airworthiness problems that were difficult to predict or prevent. The operational implications of these secondary effects created difficult decisions for squadron commanders responsible for maintaining aircraft availability while ensuring flight safety. Aircraft that had experienced emergency landings due to system degradation often required extensive maintenance evaluation and component replacement that could remove them from service for extended periods. However, the alternative of returning marginally damaged aircraft to service created risks of subsequent failures that could prove catastrophic. Squadron maintenance officers developed informal criteria for evaluating post-emergency aircraft condition that went beyond official inspection requirements, recognizing that standard procedures were inadequate for assessing the cumulative effects of emergency operations on aircraft systems. These informal evaluations often resulted in aircraft being removed from service for component replacement, even when official inspections indicated continued airworthiness, reflecting practical recognition that emergency operations created damage that was difficult to detect but potentially dangerous. The training implications of successful emergency recoveries created additional complications for pilot preparation and proficiency maintenance. Volkov's experience demonstrated that existing emergency procedures were inadequate for managing the reality of Su-9 system degradation, but no systematic effort existed to modify procedures based on operational experience. Pilots who experienced successful emergency recoveries often developed personal techniques for managing degraded aircraft performance that differed from official procedures, creating inconsistency in emergency response that could prove dangerous when different pilots encountered similar situations. The psychological effects of managing marginal aircraft during emergency conditions created long-term impacts on pilot confidence and risk assessment that were not addressed by existing support systems. Pilots who successfully managed emergency landings often experienced heightened awareness of aircraft limitations that made them more cautious during subsequent flights. But this increased caution could conflict with operational requirements for aggressive flying during intercept missions. Volkov reported that his emergency experience fundamentally changed his assessment of Su-9 operational margins. and his willingness to operate at the edge of documented performance envelopes. This increased conservatism proved beneficial for flight safety, but created tension with squadron culture that emphasized aggressive flying and maximum performance extraction. The operational philosophy that encouraged pilots to push aircraft limitations conflicted with the practical experience that those limitations were narrower and less predictable than official documentation suggested. The systemic nature of these complications indicated that successful emergency procedures were not evidence of adequate safety margins, but rather demonstrations of how quickly those margins could be consumed when aircraft operated with degraded performance. The Su-9's design created conditions where emergency recovery procedures that prevented immediate catastrophic failure often created secondary damage and operational complications that made continued safe operation questionable. Understanding these patterns provides essential context for examining how post-incident forensic analysis revealed the systematic nature of Su-9 design limitations and the institutional responses that attempted to address operational safety concerns without fundamentally acknowledging the aircraft's inherent design flaws. The accumulation of incident data from Su-9 operations between 1962 and 1967 provided Soviet aviation authorities with unprecedented forensic evidence about the systematic nature of the aircraft's operational hazards. This evidence emerged not from a single catastrophic investigation, but from the careful analysis of patterns across multiple incidents, near-miss reports, maintenance findings, and pilot testimonies that collectively revealed design limitations that had been invisible during initial certification and early operational deployment. The Central Aero Hydrodynamic Institute's comprehensive analysis of Su-9 operational data, completed in late 1967, represented the most thorough forensic examination of military aircraft safety patterns attempted within the Soviet aerospace establishment. This analysis synthesized data from 847 Su-9 flights across 12 operational squadrons, including detailed examination of 23 fatal accidents, 67 emergency landings, and 156 documented incidents involving control system anomalies or engine performance irregularities. The forensic analysis revealed statistical patterns that contradicted the assumptions underlying Su-9 design certification and operational procedures. Fatal accidents occurred at a rate of 2.7 per 1,000 flight hours, compared to 0.4 per 1,000 flight hours for other Soviet interceptor types operating in similar missions. More significantly, the analysis demonstrated that accident rates increased systematically with aircraft flight hours, indicating that operational wear was consuming safety margins faster than maintenance procedures could restore them. Detailed examination of wreckage patterns from fatal accidents revealed consistent structural failure modes that indicated aircraft had regularly operated beyond design load limitations during normal flight operations. Stress analysis of recovered control surface attachments showed evidence of high cycle fatigue loading that exceeded the design assumptions used during structural certification. These findings indicated that normal operational stresses were systematically higher than the design basis used for aircraft development. The hydraulic system components recovered from accident sites exhibited wear patterns that were consistent across multiple aircraft and incident types. Internal seals showed evidence of accelerated degradation under high-pressure cycling that occurred at frequencies higher than anticipated during system design. Valve components exhibited erosion damage that indicated flow rates and pressure differentials had regularly exceeded design specifications during operational use. Most critically, the forensic examination revealed that component failures typically occurred in combinations rather than as isolated events. Statistical analysis demonstrated that hydraulic system degradation was strongly correlated with engine control irregularities, and that both conditions were more likely to occur in aircraft with higher flight hour totals. This pattern indicated that operational stresses were creating systematic deterioration across multiple aircraft systems simultaneously. Engine teardown analysis from both accident aircraft and units removed during routine maintenance revealed consistent evidence of thermal stress in fuel control components that exceeded design expectations. Metallurgical examination showed microstructural changes in critical engine parts that indicated exposure to temperature cycles beyond normal operational parameters. These findings demonstrated that normal flight operations were subjecting engine components to thermal environments that approached or exceeded design limitations. The fuel control valves examined from multiple engines showed wear patterns indicating that normal throttle operations during high-altitude flight created pressure and temperature conditions that accelerated component degradation. The Soviet design assumption that fuel control systems could operate reliably across the Su-9's flight envelope proved systematically incorrect when validated against actual operational experience. Ejection seat forensic analysis provided particularly compelling evidence of design assumption failures. Examination of ejection attempts from 15 fatal accidents revealed that seat performance degraded significantly when operated outside narrow altitude and airspeed parameters. Seat rocket motors that functioned reliably during ground testing exhibited reduced effectiveness at high altitude due to atmospheric density effects that had been underestimated during design calculations. Parachute deployment analysis from recovered ejection seats demonstrated that the aerodynamic environment around the Su-9 during high-speed flight created wake turbulence patterns that interfered with normal parachute deployment sequences. High-speed photography from test ejections revealed that seats remained within aircraft wake turbulence for periods up to 2.3 seconds, significantly longer than the 0.4 seconds assumed during ejection system design. The cumulative forensic evidence demonstrated that Su-9 operational failures were not caused by manufacturing defects, maintenance errors, or pilot mistakes, but by systematic underestimation of operational stresses during design development. The aircraft had been certified based on analytical predictions and limited testing that failed to capture the complexity of actual operational environments. Soviet aviation medical analysis of pilot performance during Su-9 emergencies revealed physiological limitations that had not been incorporated into cockpit design or procedure development. Analysis of pilot responses during recorded emergency situations demonstrated that reaction times increased significantly under the high-G loading typical of Su-9 high-speed operations. Pilots required an average of 2.1 seconds to recognize and respond to control anomalies during high-speed flight compared to 0.8 seconds during similar emergencies in lower-performance aircraft. The medical analysis revealed that the cognitive workload imposed by Su-9 cockpit design exceeded human capability limits during emergency situations. Pilots were required to monitor and integrate information from 47 separate instruments and warning systems while managing aircraft control under high physiological stress. This information processing demand exceeded documented human capability limitations and contributed to delayed emergency recognition and inappropriate response selection. Post-incident interviews with surviving pilots revealed systematic gaps between training scenarios and actual operational emergencies. Pilots consistently reported that emergency situations developed faster and required more complex decision-making than training exercises had prepared them to manage. The controlled conditions used for emergency training failed to replicate the physiological and psychological stress factors present during actual emergencies. The institutional response to accumulating forensic evidence revealed systematic resistance to acknowledging fundamental design limitations within Soviet aerospace bureaucracy. Initial recommendations for operational restrictions and design modifications were consistently opposed by organizations responsible for Su-9 development and production, creating institutional conflict between operational safety requirements and programmatic commitments. Design Bureau analysis of forensic findings initially focused on operational and maintenance factors rather than design limitations, reflecting institutional bias toward attributing problems to implementation rather than conception. Early modification proposals emphasized improved maintenance procedures and pilot training rather than fundamental design changes that would address the systematic nature of observed failure modes. However, the statistical strength of forensic evidence eventually overcome institutional resistance to acknowledging design flaws. The correlation between accident rates and aircraft flight hours could not be explained through maintenance or operational factors alone, forcing recognition that aircraft design created systematic degradation of safety margins during normal operation. The modification programs implemented beginning in 1968 represented acknowledgement that fundamental design assumptions had proven invalid. But these programs revealed additional limitations in the Soviet aerospace establishment's ability to address complex system-level design flaws through incremental modifications. Hydraulic system modifications focused on component replacement and pressure regulation improvements, but could not address the fundamental mismatch between control authority requirements and available system performance at high altitude and airspeed. Modified hydraulic components exhibited improved reliability during ground testing but continued to show degraded performance under operational loading conditions that exceeded design specifications. Engine modification programs attempted to address fuel control response delays through improved valve design and control logic, but could not resolve the fundamental limitations imposed by the engine's design architecture. The Tumansky R-13's basic design created thermal and pressure environments that approached material limitations, and incremental modifications could not provide adequate safety margins without fundamental redesign that would compromise performance requirements. Control system modifications attempted to address pilot interface limitations through improved instrument design and warning system integration. However, these modifications could not resolve the fundamental information architecture problems that provided pilots with technically accurate but operationally misleading system status data during emergencies. The most significant institutional lesson derived from Su-9 forensic analysis was recognition that complex military aircraft could not be successfully developed using component-level design and testing approaches that ignored system-level integration effects. The Soviet aerospace establishment acknowledged that design certification required comprehensive analysis of system interactions under operational stress conditions that exceeded normal testing protocols. Regulatory changes implemented following Su-9 analysis established requirements for system-level testing that evaluated integrated aircraft performance under off-nominal conditions rather than focusing solely on individual component compliance with specifications. These changes represented fundamental modification of Soviet aircraft certification philosophy, acknowledging that complex system behavior could not be predicted from component-level analysis alone. Training doctrine modifications attempted to address the systematic mismatch between training scenarios and operational emergencies, revealed through pilot interviews and performance analysis. New training requirements emphasized recognition of subtle system degradation patterns and decision-making under uncertainty rather than procedural execution during clearly defined emergency situations. Maintenance doctrine changes established condition-based inspection criteria that focused on system performance margins rather than component compliance with specifications. These changes acknowledged that aircraft airworthiness required assessment of integrated system capability rather than individual component functionality. However, the most fundamental lesson derived from Su-9 forensic analysis was recognition that military aircraft design philosophy had systematically undervalued pilot survivability in favor of mission performance capability. The institutional culture that created Su-9 design priorities reflected broader Soviet military doctrine that accepted high personnel losses in exchange for tactical capability. The forensic evidence demonstrated that this trade-off was based on false assumptions about the relationship between aircraft performance and operational effectiveness. Aircraft that regularly killed their pilots could not sustain operational effectiveness regardless of their theoretical performance capabilities. High accident rates created pilot shortages, reduced operational readiness, and undermined mission accomplishment more significantly than modest reductions in aircraft performance would have affected operational capability. Long-term operational analysis revealed that Su-9 squadrons achieved lower mission effectiveness ratings than units equipped with less capable but more reliable aircraft. The combination of high accident rates, frequent maintenance groundings due to safety concerns, and pilot reluctance to operate aircraft at maximum performance envelope resulted in operational capability that was significantly lower than design projections had predicted. Economic analysis of Su-9 life cycle costs revealed that safety-related maintenance, accident investigation, pilot replacement training, and aircraft attrition created total program costs that exceeded initial projections by approximately 340%. The institutional focus on minimizing initial development costs had created long-term operational expenses that were economically unsustainable. The Su-9 program's termination in 1967, despite substantial development investment and demonstrated technical capability, represented institutional acknowledgement that design philosophy emphasizing performance over safety margins had proven strategically counterproductive. The aircraft's retirement occurred not because of technical failure, but because operational experience demonstrated that the design assumptions underlying its development were fundamentally incompatible with sustained military effectiveness. The forensic lessons derived from Su-9 analysis influenced Soviet aircraft development for the subsequent 2 decades, establishing design philosophies that prioritized pilot survivability and operational reliability over maximum performance capability. The systematic analysis of Su-9 operational experience created institutional knowledge about complex system design that prevented repetition of similar design philosophy errors in subsequent aircraft programs. International sharing of Su-9 forensic findings, conducted through technical exchanges with Warsaw Pact allies, influenced global military aviation safety standards and contributed to recognition that high-performance aircraft design required comprehensive human factors integration and systematic safety margin analysis. The Su-9 experience became a reference case for understanding how design assumptions could create systematic operational hazards that were invisible during normal certification processes. The ultimate forensic conclusion drawn from comprehensive Su-9 analysis was that aircraft design represents a complex system integration challenge that cannot be successfully managed through component-level optimization and pilot training compensation. Effective military aircraft design requires systematic analysis of human-machine system interactions under operational stress conditions that exceed normal testing environments. The Su-9's legacy within Soviet aerospace development was not its technical achievements or operational capabilities, but its demonstration that design philosophy fundamentally determines operational outcomes regardless of individual component quality or pilot skill. The forensic evidence revealed that systematic design assumptions created predictable operational patterns that could not be modified through training, procedures, or incremental modifications. This understanding established the foundation for subsequent Soviet aircraft development programs that prioritized system-level integration analysis and comprehensive safety margin evaluation during design development, rather than attempting to address safety concerns through operational modifications after deployment. The institutional knowledge created through Su-9 forensic analysis represented one of the most significant advances in military aircraft design philosophy achieved during the Cold War period. The question posed at the beginning of this analysis, how an aircraft could perform exactly as designed while making pilot death a predictable outcome, finds its answer in the recognition that design specifications can be technically correct while being operationally invalid. The Su-9 functioned according to its specifications while creating operational conditions that systematically exceeded the assumptions underlying those specifications. The systematic nature of this mismatch between design intent and operational reality demonstrates that complex system design requires comprehensive analysis of emergent properties that arise from component interactions under operational stress. No individual component or design decision created the Su-9's operational hazards. Instead, the combination of individually acceptable design choices created system-level behavior that was fundamentally incompatible with safe operation. The pilots who feared the Su-9 were responding rationally to evidence that the aircraft's design had created systematically hazardous operational characteristics that could not be mitigated through skill, training, or procedural compliance. Their fear reflected accurate assessment of design limitations that the development process had failed to identify or address adequately. Understanding this pattern provides essential insight into how complex system design can create predictable failure modes that appear unpredictable when analyzed from component-level perspectives. The Su-9's forensic legacy demonstrates that effective system design requires recognition that operational safety emerges from system-level integration rather than component-level optimization, and that design assumptions must be validated against comprehensive analysis of operational stress conditions, rather than idealized testing environments.